Hi, good afternoon, everyone. My name is Shyjumon, basically from Intel. I would like to get through some of the things which is around Intel Optane. So the topic is basically Intel Optane SSD performance analysis on Android. I think so far the sessions you have been listening about the hardwares and the hardware capabilities. I don't talk too much about the hardware capabilities. I would rather because Optane is pretty much familiar with all of you. So I would try to get my presentation more focused on the advantages of Optane and some of the use cases of Optane and how we are going to utilize that in the low power segment. Okay, so this is what the agenda is set for today. A brief introduction about Optane, the people who are interested to know a bit more about Optane. I'll give you a very brief introduction on the hardware capabilities and what it's meant for, and what is the motivation for us to take that into the low power segments. Okay, and then a brief on the software stack, and we wanted to present some of the performance numbers and performance analysis, and how you can actually make use of Optane in the low power segment, especially in Android kind of an environment. Okay, and bit of some conclusions and recommendations. Okay, so this is what Intel was doing so far in the NVMe technology industry. So Intel was kind of demonstrating with the innovations what we can bring in on board for the NVMe. So we started up with the 3x nanometer, that is the 34 nanometer in 2008, and paused with 25 nanometer chips came in. And in 2015, eventually we come up with the Optane technology. So this is the highest density 3D NAND technology, what we have introduced. And it's totally a different class of technology where we are going to redefine all the conventional, conventional notion on the NAND and around the storage. Okay, and going further, we have come up with the TLC, 64-layer TLC consumer SSDs, and the rulers are coming. And then the QLC NAND technologies. And at present, we are focusing on the Optane persistent memory, that is called DC persistent memory, Optane DC persistent memory, which is more of presently used in the server side. And then we have the enterprise data SSD form factor, EDSSF products, which is kind of coming up. Okay, this is what the portfolio, just to bring in you. Okay, so I think most of you are pretty familiar with what is an Optane media technologies, right? So, apart from the conventional NAND technology, we have come up with a cross-point structure. So I'll take a minute to I think most of you are aware of it, right? So it's basically a cross-point structure where we have captured the cells, and on top of that, we have a selector. Okay, if you take this in one unit, it is comprises of a cell and a selector, and which is connected with perpendicular lines that we call it as crossover wires. Okay, so I'll come to the comparison with the DRAM and NAND in the next slide. Before going to that, so you can see that the main attraction is that it's scalable. It's a 3D architecture, and the unit cells are accessed through the selectors and the cross wires. So it's it's stacked in the 3D manner, and there is no transistors involved. Okay, and the materials are really breakthrough materials, which is capable to switch, and you can address bit bytes. Okay, and of course of that, and also because of the material property and the interlaying semiconductor property, it is obviously high performing. Okay, this I just took, basically to understand how do we stand out in terms of an Intel Optane technology in comparison with a NAND or a DRAM technology. People might think that why do I compare a storage technology with a DRAM? The answer is from the figure itself, that I can access bit or bytes. It's not just about block access. Rather, I have pain for accessing in block. Okay, so what is an Intel Optane is? It's nothing but the Intel Optane memory media plus an intercontroller. So this is what makes an Intel Optane SSD. Okay, and it can be compared with a 3D NAND or a TLC, MLC, SLC NAND in terms of a storage technology perspective, and it can be even compared with a DRAM in terms of, memory perspective. So I will take the next, where actually how do we access this memory? We have the option to access it in a bit-wide access, and also we have a block emulation inside it that makes it qualified for an SSD. And if you compare it with a NAND, it's just like block access, where in DRAM you have bit-wide access, right? So how do we store things? It uses a bulk material property change. The material itself changes based on whatever the voltage levels coming in between those crossovers. It will change the property of the material itself to store the data, rather as compared to a stores, floating gate approach in the NAND or in the capacitive approach in the DRAMs. Okay, and the interface part, we have NVMe and we have an interface called DIMM. NVDIMM interfaces, which is also common now. And in terms of a NAND, you have NVMe, SAS, SATA, all those interfaces. And the best part is we don't have any firmwares, and we directly use the ASIC-based hardware programming, and there is no DRAM. So if I say, there is no DRAM, that means that you're going to get almost similar performance on the workloads what we are going to choose, and also based on the age of the device. There is not much performance differences you can observe. So this is what the memory and storage hierarchy inclusive of Intel Optane. So I would point that where and all we can introduce Optane, this new media. So basically I have categorized it into a hot and warm sectors of the memory. So wherein in the warm, hot segment, we have something called an Optane DC persistent memory, which will boost your DRAM, or you can say that it's going to give you an extended DRAM. Then we have Optane DC solid state drives, which is going to come on top of your Intel 3D NAND based SSDs. So, this is going to boost our, storage space, and which is much faster than what we have in the conventional NAND SSDs. So these are some of the latency numbers. I hope you're already aware of this. Still, for the interest of the topic and to keep the topic oriented, I would like to share a few minutes here. So when we started with the SDD technologies, major bottleneck we had was the media latency, right? Then we have you can see these colors, like blue stands for the media latency, and the orange stands for the interface latencies, and the green stands for the software latencies. Okay, so when we come up with the SSDs, basically the SAS and SATA based SSDs, we could actually reduce or half the media latency. And when it comes with the NVMe, you can see that the oranges disappear. So that means we have solved a lot of problems which was there in the interfacing technologies, especially HBAs and HBS majorly. Okay, right? So now when it comes to Optane, we further reduce the media latency, right? So the main points I want to highlight here is like it's Optane gives 10x reduction in latency versus any of the standard class NAND technology devices, any of the SSDs we could able to achieve about 10x. NVMe has already reduced, and we further reduce, right? So going further, this is the typical Linux software stack. So I just wanted to give what is the difference between an Optane as an SSD and Optane as a persistent memory, or rather we can call it as a persistent memory based SSDs nowadays, right? So Optane as an SSD has changed, nothing changed in the software stack. So it's all the traditional software stack where you have your standard file APIs, then you have your file system block layers and the driver and the block layers. and then you're going to access the storage, right? So it's a typical use case wherein you here the media plays a role, but I cannot say that it's going to give a massive performance improvement, right? So we can see it on the applications and the workloads which I'm going to exercise in the further slides. But I would say that this is a typical replacement of a normal SSD. And you know that an Optane is coming in an M.2 form factor. You can replace any of your M.2 drives with the Optane without any changes. And also, standard Linux NVMe driver is already compatible with Optane, and we are providing enough support in the open source community. So coming to the Intel Optane persistent memory aspect. So it is going to change the entire software stack. In fact, it's already changed. Everything is mainline, and Linux community has also accepted the persistent memory related things. You know about the DAX also, right? Direct access. Okay, so in this context, basically, it's going to replace the traditional file system. In fact, traditional file systems like ext4 and XFS has already adopted the persistent memory. Okay, so it is going to bypass all our page cache and the block layers. It is directly going to access the memory mapped pages from the application itself with the load and store instructions. So this is gone, underlying we have an NVMe driver. So you're going to get a /dev pmem0 or something. And you can, now we have options in the Linux where you can mount with mount-o DAX. You give it, it is pretty much like a drive you can use with the persistent memory. Again, a couple of other modifications which recently Linux has adopted is that in the mmap system call, we have a flag called map_sync, which enables the applications to request that, okay, I need to use the persistent memory properties. So, but it's again the call of the file system to decide whether to grant or not, whether to save or not. All those things are already mainline, and it's gonna give you an edge on performance for no doubt. So here in the Intel Optane SSD part, we are only having the advantages of the media and the workloads how we are going to give. Where in the Intel persistent memory concept, if you take it in an SSD, there is a drastic change. Because we could able to reduce the green, which I was showing in the earlier slide. The green is not reduced over the period. So with this, we can reduce the green. That means the software latencies are also getting reduced. Okay, so now I'll take you to the Android stack. I don't know how many of you are familiar with the Android kind of environment. I hope everybody is using an Android phone. So our major problem today, what is our major problem? One is WhatsApp, right? WhatsApp, people are forwarding you multiple things and it's going to create multiple copies. Your storage is screwed up, right? And you're forwarding something, WhatsApp is going to store that also. And when you browse something, your DBs are getting filled, right? So I would like to categorize the Android IO stack in terms of a storage perspective, that we have a DBMS, that is the SQLite DBMS, which has been used in the Android, SQLite's database. Then we have the file system. Most of the Android devices coming up with ext4 as the file system. There are F2FS also. People are using these days only for the user data partitions. And there is an IO daemon. There is IO daemons, in fact, like MMCQD, and there is a storage daemon which is going to keep track of your health conditions of the storage and how the allocations are happening and all those stuff. And stats, definitely. And there is IO scheduler. So this is the typical Android stack. So what we could understand from this Android performance analysis in terms of storage usage, what we understood that 50% of the writes which is happening is the ext4 journal update. And almost 60 to 80% of the writes are random writes, excluding the metadata and journal updates. 60 to 80% of the writes are random. I'm just building here. This is basically important for us to take to the next slide, where actually we are going to talk how we selected Optane as the media in Android. Okay, so and also we can observe that most of the IO requests are 4 KB, and more than 50% of the writes are synchronous in nature, and almost 70% of the writes are 4 KB IO writes. And It's a deadly combination. You have an SQLite database and ext4 file system, which is going to trigger at least 3 times fsync for a single operation. Or maybe if I say SQLite database update or an insert, it's going to cost you around 11 writes to the SSD. So it's not only impacting on the performance of the SSD, but it's also going to impact the life of the SSDs, because we are going to have a very eccentric write cycles. So, and unfortunately in Android, every application uses SQLite database. And if you see, one application, let's say for example, we have categorized multiple applications. We have taken SNS like Facebook, WhatsApp, and all those things. And we have also taken the contacts, SMS kind of traditional applications. We have taken the web-based applications. What we can see is that, everybody uses SQLite database, and that too multiple databases. For example, if you take the example of a contact, so you're going to update your contact, it's going to access the contact DB, and to view the contacts, so you're going to access the settings DB. So you mean to say that in Android you will find lot of DBs which is spread across, and all the applications are going to use those DBs for different updates and things like that. And if you take the example of a multimedia file, it's going to take the media DB, and it's going to take the tiling for the gallery DB. Like that, hell lot of DB operations are happening. So what we understood is that it's like SQLite writes are the major activity happening in the Android, which is almost like 80 to 90% of the writes are going to be the SQLite, and which is going to take one operation of SQLite is going to take at least 11 cycles of the write cycles of our SSD. So it's you might have observed that our phones, when we buy it, it is going to give you a very good performance in terms of search, or in, if you want, nowadays we don't really care how many SMS is coming, right? So you have a hell lot of SMS. Out of those SMS, you wanted to search something, you're going to take a hell lot of time. And what you can observe, the other thing is that you bought a phone today, and after 6 months you get one performance, and after 1 year you get another performance. So SSD is also, to say that the storage is also going to play a lot of things. So most of the phones are coming with eMMC or the UFS. So, and the SSD form factor, why we are talking here, and especially the Optane kind of things, because the next Android is going to be the automotive Android, right? So where actually you're going to have around 4 TB per day data on your car every day, right? So you imagine what are the telemetric data coming, and what is the navigation data coming, and what is the media content you're going to use, and how many, nowadays people use only video calls, right? So how much streaming data is going to come, and people are going to, multiple displays are there. Some of the people sitting in the back side might be watching YouTube, some might be watching front side, they might be watching video. So it's going to be like a huge volume of data which is going to be there in your automotive Android. So we took like, we tried to do the traditional performance analysis. So that is what I was saying, that most of the, in the previous slide if you see, around, you can see that 60 to 80% of the writes are random write. So we took the analysis to see that how my random read and write is performing. Okay, so by switching to Intel Optane M10 series, which is the primary series, we have an M15 series which is coming into the market, which is much better. So I would say that 70% improvement in the write, and I could get almost like 50% improvement in the, 70% in the read and 50% in the write. When I used a Q depth of 4, that much sufficient it was to get this much numbers. So, Optane has given me a boost in the random write, which is going to solve my problem of 60 to 80% of my workloads. Now, there is not much sequential impact, and it was at par. We just measured it because we wanted to make sure that, because of shifting to Optane, I haven't screwed up my sequential performance. So we just made it clear that, okay, there is no performance impacts which has been happened in sequential, but sequential can also grow up, in the next gen of Optane series. So we haven't focused on sequential, because we were majorly targeting on the server side, and then we were targeting on these kind of workloads, which I was mentioning in the Android. So this is the real booster, I would say. So this data is basically measured with, Android standard SQLite benchmark. So what I could see is that just by replacing to Optane, I could get around 90% improvement in the, database performance. So as I said, in Android, everything is database centric. So you're going to get impact on all the applications, all the transactions which is happening, and escalators having the bad habit of creating, even temporary DB files, and short-lived files are there, right? So all those are getting impacted, and we could see that Optane is providing me around 90% of the impact. So where do I get directly the advantage of this? Basically, I can see a lot of difference in the app launch time. Like the time which required for a tap to the application to come up. So that's what we call it as an app launch time. You can categorize it into two categories. One is like for the first time you're doing it, or maybe after a reboot you're going to press for the first time, or you are already used and you press the back button and then you're going to relaunch it. So relaunch is pretty much like, everywhere you get a shorter time, and for the fresh launch you'll get, a lot of launch time, right? So you may have to wait for the application to get loaded. So this is the right away measure of what we are observing in the performance of the database, okay? And also like, when you have your phone went for an update, or maybe you just unboxed your phone and you're going to take it and you're going to launch an application, what will happen is that there is a lot of, disk-centric operations are happening, because Android uses something called a Git and AOT, that is the compilation, Java compilers. So that is like just-in-time compilation and ahead-of-time compilation. So in case of just-in-time compilation, what happens is that you're going to unpack certain things based on the windows or the layouts you're going to explore. So those kind of environment, you will get real boost because of this, database improvements. And this is basically the data of the boot time. So, typically, how much time a phone or an Android device required to boot from power off to the, full UI. This is what we have measured here. So, it is a combination of all the advantages, whatever we have discussed so far. Like, database gets involved, and also all the read writes gets involved, and latencies gets involved, queue utilization gets involved. So altogether, what I would say is that we have observed around 20% improvement in terms of the call boot time. So, this is like a call boot time 20% meant a lot for all the users, especially if you try to imagine you have an Android system which is going to give you a rear view mirror image, rear view cameras data to your automotive system. So the moment you put the reverse gear, you need to get the camera up and running, and it need to be shown, right? So that is one of the typical use case where actually you will find the advantage of this kind of environment, and wherein you don't, in an automotive environment, you don't have any other choice. It's like a real time scenario. So if your camera gets stuck there, so what is going to happen is you can't do reverse, or you can't do parking. So you're going to be in a situation. So this is basically leading to such kind of real use cases, I would say. So these are some of the data which we have collected from one of the firm called Shrout Research. So you can see that they have exercised Optane in the image processing workloads and graphics workloads with Houdini, and we have also measured the TBW factors. So you can see that compared to IPAR memories, we can see that it's almost giving you more than 50% in both the image processing and the graphics processing workloads, and also you can see that the endurance is too good. So let's say, for example, most of the drives, especially the flash drives, what we have today is having like 10,000 P cycles. That's a kind of life, right? So Optane can provide you 1,000 times of that. So basically, I mean, and Optane, when I use Optane in Android kind of an environment, so wherein actually the writes are so much and very, I mean, like as I mentioned, 60 to 80% random writes are happening. It's anyways not going to be healthy for the storage device. So where I'm getting 1,000 times better endurance, that's going to matter a lot. And the other thing is that we are going to get the similar kind of performance throughout the life of the device. So that means you don't need to worry that your phone is behaving today differently and tomorrow it is behaving differently. Those kind of problems also address. So these are some of the numbers which is basically explaining you about the, I mean, image processing capabilities and graphics capabilities. So, I mean, so what I would try to conclude here is like Optane technology is best suited for the database kind of workloads, as you have seen the numbers. And Android applications are extensively using the SQLite. And Optane can do, I mean, much better performance even in the low power segment. You know that Optane is already in place in the server market and which has been used in the persistent memories and which has been used in the farms, storage farms and all. So here we say that, I mean, there is no power impacts and it can be well suited for the low power segments. And all Android storage overheads, whatever I have shown you earlier, that SQLite DB related or the file system related or the IO daemon related, everything has been improved with the replacement of the SSD with the Optane SSD. So these are some of the future application scope, what we could identify based out on our analysis and the measurements. What I would say is that massive in-memory database, fast system recovery. So I talked about the boot time and the same time you can even measure it on the recovery time. And low latency, high endurance. These are the key terms. So as I mentioned that we have analyzed the, I mean, Android application space, the simple applications like contacts or SMS, and then the multimedia applications like a camera or a camcorder or a gallery kind of applications. And we also checked some of the games, like popular games like Angry Bird, I mean, all those games. So basically it is giving much better performance in terms of gaming. So it can be very much useful for the gaming and high fidelity pattern recognition. You have seen the image processing workloads. And we also experimented with some of the neural network things and also with the AI chips like, I mean, Movidius and all. So you can see better response in terms of a storage response is concerned. And there are a couple of genomics research which is going around because of the, I mean, abnormal considerations of the material. They are trying to use it for, I mean, some purposes. So there are certain research papers, I'm not quoting that. Okay, I think that's it, and these are some of the data, basically, I mean, how we perform the performance analysis and what are the measurements we have done. And these are the workloads we have selected. So, I mean, I think it will be available to the handouts. And this is a system configuration which we have used. So that KBL NUC is a, I mean, commercial small box PC kind of thing which has all the flexibilities. I mean, you can buy it online and also like, I mean, if you wanted to develop something, it has almost all the options available for us to play around. And we have used Android Oreo version. I mean, that was the latest the time we were using. And these are some of the resources which is available. So we have an evaluation guide of Intel Optane available in the web. And there is an open source Android version of Intel is available. So this is called Celadon. So you can basically download and build it for any Intel platform. So it's like Ubuntu. So you can just download and start your Android. That's it. Open for questions. We have the lowest capacity starting from 32 GB, and we have up to 512.
I have a question here.
Okay, sorry.
Yeah. You were talking about Android and automotive, right? So there you were planning to deploy Intel processors, or Android is usually popular on ARM-based chipsets, right?
Intel Android is already there. That's what I was, so you can get it from here. This is the Android version. We call it Celadon. I mean, we are supporting in almost all the SOCs, which is
Is there a
available in the
reference
market.
board, something like Beagle or something? Is there a reference board for Intel Android?
Basically, right now you can get it for Apollo NAC,
Uh-huh.
Apollo Lake NAC. So
Uh-huh.
this is called APL NUC,
Okay.
and there is a version called KBL, KB Lake NAC. So that is also like full-fledged. It's all high compute devices, big core systems. So Apollo Lake is a little bit low core system. KBL is the middle, and we are coming up with more SOCs in that.
Okay. Thank you.
Yeah. Yep. So basically, we are trying to understand what is the, what is the life of your one block in the disk. So it's a standard hardware test which is conducted across. No, this is not with FIO. FIO is used for, the read-write workloads only. Random and sequential read-write only we have used FIO. Otherwise, those tests are not with FIO. Even this is with SQLite separate. It is also not with FIO.
While doing performance analysis, can you show some light on that what were the parameters which were used for performance analysis? And apart from FIO, have you tested with some other tools, or
Right.
what was your benchmarking strategy? If you
See,
can throw light on that.
mainly we have used FIO because if you see the Android present stack, we have FIO adopted in the Android stack. If you see the external folder, you find the FIO, which has been standardly adopted. So we have used other things like normal DD commands we have used. And also we have done kind of drive level that, we put code in the drive itself and try to see that in various layers. And also we have used the mobile storage analyzer tool that is called MOST, M-O-S-T. So that you can evaluate all the entire stack, and you can even differentiate which PID gives you what kind of load, and you can clearly monitor that. And apart from that, this is like an Intel's QA tool, which we have used for the call boot analysis. And SQLite, we have used the SQLite benchmarker, which is also available in Play Store.
So for fault injection tests, so were some tests performed for negative testing, or in the case when system crashes?
Yes,
Or
here I was not focusing on that, but we do have that kind of testing. All the drive qualification tests we have.
thanks.
Oh,
Right. So we have compared with multiple SSDs. We try to take the similar kind of, SSDs, which is like mostly we have used NVMe based. No, I haven't compared the wear level aspects for this particular presentation. We have, we have certain data. I'm not sure whether, something is available in the public forum or not. So it's also been compared. So I would say that, wear leveling is also far better. Because if you see the TBW numbers, you can even make out from there, right?
so in your automobile solution, are you planning to use DRAM also, or?
I would say that, automotive Android, whatever the stock Android is giving, the same thing you can find it, same which is tuned for the Intel architecture, that's you can find it in the Celadon site. Which is basically a GitHub, so you have all the code also there.
Basically, I want to know the cost comparison also, having DRAM and SSD together and replacing just by Optane.
Yes, I would
Any
say
cost
that,
benefit?
I mean, if you have Optane SSD, and let's say you plan to do 8 GB DRAM, so you could probably conclude for a 4 GB DRAM and an SSD, and probably you can think of a swap space on Optane. So this combinations can work well. We have, I mean,
Cost
a
would be the
couple of
same.
things are there in that. Yeah. See, let's say if you're going to plan a bomb where actually you're going to target an 8 GB DRAM and you're going to have a, let's say, 32 GB SSD or something. So what I mean to say is that because of the performance, why we are going for an 8 GB DRAM is we want to have the, I mean, RAM availability high to give the support of the Android's multitasking, right? Android requests at least 6 background application to be holded and relaunches and all those things. So if you replace or come with Optane, so what I would suggest the configuration, roughly 4 GB DRAM, and rest you can use as an Optane SSD. And if you can configure a swap space on Optane, so it's gonna solve your both problems.
So cost-wise is the question.
Cost-wise, I'm not pretty sure, but I would say that it will stay in between DRAM and SSD. Yeah, it is more than SSDs, whatever it is. But it's coming down because of the process improvements which is happening. We call it as a Intel Optane memory media. So that is what I was saying about that, I mean, 3D cross architecture. No. Basically, it's altogether a different semiconductor itself. It is not NAND based. What we did is like we sliced it out and we made it like a single unit cells and stacked it up. So the point there is like, I mean, we are actually doing block emulation. It is not as such a block. So rather we would be getting much better performance when we go it in a byte-wise or a bit-wise access there. Yeah, it's been adopted with the NVMe 1.3 standard. It is already there. Yes, yes, NVMe standards are already there. I'm not. No, it won't apply. Right. Yes. So basically, what I mean to say is that NVMe 1.3 standard onwards, Optane has given certain commands which has been accepted and which has been already included in the Linux space in a software aspect. In the hardware perspective, I don't think we need to, I mean, expose something to the public forums, right? Yeah, persistent memory has been already adopted in server market, many of the places, and also like as I mentioned, like recent Linux adoption, wherein ext4 is adopted, XFS is adopted. In terms of file system, and also there is a system call modification that is on the AMAP. I would say the map underscore sync. That is a flag has been introduced. Not really. SNIA is supporting us a lot in the NVM programming. Otherwise, I don't have any numbers. Mobile is not I'll just finish this question. Okay, so mobile is not a target area. In general, we are seeing that how we can utilize it in the operating system. We have taken Android as an operating system. We just wanted to say that it can be adaptable to a mobile operating system. It can be adaptable to a GPOS. It can be adaptable to a cloud-based or a container-based systems. So this is what our interest is. We are not emphasizing anything on the mobile operating system or in mobiles. Okay. I think it's time off. Thank you all. Thank you for listening to me.